Welcome to my demonstration of a DirectX 11 3D project. In this showcase, I am excited to present a stunning collection of techniques that push the boundaries of visual innovation. Prepare to be amazed as I reveal the impressive capabilities of real-time rendering, dynamic lighting, advanced shaders, tessellation, and post-processing effects. Join me on this immersive journey into the limitless realms of creativity and experience firsthand the incredible possibilities that DirectX 11 offers. Welcome to the future of 3D technology, as seen through my eyes. Deferred rendering is a graphics technique used to efficiently render complex scenes with multiple light sources and materials. It divides the rendering process into two stages, geometry and shading. During the geometry stage, the scene is rendered into an intermediate buffer called the G-buffer. The G-buffer stores pixel information such as position, normal, color, and material properties. This step only needs to be performed once, regardless of the number of lights in the scene. In the shading stage, the G-buffer is utilized to calculate lighting for each pixel. Unlike traditional rendering techniques, deferred rendering applies lighting calculations only to visible pixels stored in the G-buffer. This significantly reduces the computational load and allows for a larger number of dynamic lights without sacrificing real-time performance. Shadow mapping is a technique used in computer graphics to simulate realistic shadows in 3D scenes. It involves rendering a depth map from the perspective of a light source and then using that map to determine which areas of the scene are in shadow. To create a shadow map, the scene is rendered from the viewpoint of a light source. Instead of rendering color information, the depth information is stored in a texture called the shadow map. The depth values represent the distance from the light source to each point in the scene. When rendering the final scene from the camera's viewpoint, each pixel's position is transformed into the light's coordinate space. The corresponding depth value from the shadow map is then compared with the transformed depth of the pixel. If the pixel's depth is greater than the depth stored in the shadow map, it means the pixel is occluded by an object and is therefore in shadow. Tessellation is a computer graphics technique that subdivides polygons in a 3D mesh to create more detailed surfaces. By adding smaller triangles or polygons, tessellation enhances the visual quality and realism of objects. It is used to generate smoother curves, sharp edges, and intricate surface details. Tessellation is particularly useful for rendering detailed objects and organic shapes. It can be uniform, where polygons are divided into equal-sized parts, or adaptive, where the level of detail varies based on factors like distance or curvature. Tessellation provides a significant improvement in visual quality but requires additional computational resources and careful optimization. LOD, or level of detail, is a technique that adjusts the level of detail of objects based on their distance from the viewer. It is employed to optimize performance by reducing the complexity of distant objects while maintaining high detail for those closer to the viewer. Dynamic cubic environment mapping is a technique used in computer graphics to create realistic reflections on surfaces. It is particularly useful for rendering reflective objects and adding visual depth to scenes. The technique involves projecting the surrounding environment onto an object's surface using a cube map, which is a texture with 6 faces representing different directions. To implement dynamic cubic environment mapping, you would first generate a cube map by rendering the environment from multiple camera viewpoints onto the faces of the cube map texture. This captures the color and depth information of the surroundings. In the rendering process, the cube map texture is then mapped onto the object's surface. Using the world space reflection vector in the pixel shader, the corresponding pixel color is sampled from the cube map texture. This sampled color is used to calculate the reflection color for each fragment on the object's surface. Frustum culling using a spatial tree is a technique used in computer graphics to improve rendering performance. The frustum represents the visible area in the camera's view, and the spatial tree is a hierarchical data structure that organizes objects based on their spatial relationships. In frustum culling, the algorithm starts at the root of the spatial tree and checks if each node's bounding volume intersects with the frustum. If a node is completely outside the frustum, the algorithm can quickly discard the entire subtree rooted at that node, as none of the objects in that subtree are visible. This technique helps reduce the number of objects that need to be processed and rendered, resulting in faster rendering times and improved performance. By selectively excluding non-visible objects from the rendering process, resources are focused on rendering only what is necessary, making the overall rendering pipeline more efficient. In simpler terms, frustum culling using a spatial tree is like quickly removing entire groups of objects that are completely outside of the camera's view, so that the rendering engine doesn't waste time and resources on rendering things that the player or viewer cannot see. A particle system is a technique used in computer graphics to simulate and render a large number of small, independent entities called particles. These particles can represent various visual effects such as fire, smoke, explosions, or even raindrops. Each particle has properties like position, velocity, size, color, and lifespan. The system updates and animates these particles over time, creating dynamic and realistic visual effects. A billboard is a technique used to render 2D objects or sprites in a 3D scene, maintaining the illusion of a 3D environment. It involves creating a flat, rectangular plane that always faces the camera, no matter how the camera or the viewer moves. This technique is often used for rendering objects like trees, clouds, or signs in a 3D scene. By aligning the billboard with the camera's view, it gives the impression that the object is three-dimensional and facing the viewer, even though it is just a 2D image.